Hi everyone, my name is Romain Michon and I'm part of the Faust core team. This presentation, which is actually a tutorial, is going to be about the Faust physical modeling toolkit. There are multiple goals for this workshop. The first one is to give you an overview, a historical overview of the things that we've been developing as part of Faust for physical modeling for the past 10 years. We will mostly focus on the Faust physical modeling library, which is a library for waveguide and model physical modeling in Faust. And we will also be looking at Mesh to Faust, which is a tool that can be used to turn 3D meshes into model physical models that can then be used with the Faust physical modeling library to implement all sorts of musical instruments in Faust. So this tutorial is targeting pretty much any kind of audience. So we will start slowly by giving you some reminders about physical modeling in general, and mostly looking at waveguide and model physical modeling. And then we will go into more details and look at how these different tools actually work. And so the Faust physical modeling library, which is the first thing we're going to look at in this tutorial, is a library that allows you to implement physical models of musical instruments using waveguide physical modeling and model physical modeling, but in a modular way. So you'll see that we have mouthpieces, we have strings, we have bodies of musical instruments that can all be connected together in many different ways and in a completely modular way, which was not the case of the original Faust SDK. And this is going to be what the first part of this tutorial is going to be about. Okay, so before I move on to this, I just want to give you some reminders about waveguide physical modeling, because I'm pretty sure that some of you here don't really know how it works. So this tutorial is not about teaching you waveguide physical modeling, of course, but I just want to remind you about how that works. So if you look at the diagram here on the screen, you will see a waveguide model implemented. Well, here it's not implemented, but it's a waveguide model of potentially a string. And so the first thing that we need to ask here is, what is a waveguide? So a waveguide is just a structure that guides waves. That's it, And in any medium that you might use, like whether it's a string, it's a plate, or it's a tube or whatever, the material, the medium that you're using to drive the wave is going to have an impact on the time it takes for the wave to go from point A to point B. And depending on the material, it might go faster or slower, So basically, in signal processing and in the way we're going to implement that in Faust, a waveguide is just two delay lines in parallel. Because if you pluck a string, like if you take a string and then you pluck it, you will create two waves which are going to go in two opposite directions. One is going to go to the left, one is going to go to the right. So if you want to implement the most basic string physical model in the world, you need to implement first the fact that these two waves are going to go in two different directions. And on the diagram that you see here, the waves which are going to go on the right are implemented here at the top of the block diagram by two delay lines, the first one and the second one here. And we'll see later why there are two delay lines. And then waves which are going to go from right to left are implemented here on the diagram with the two delay lines which are at the bottom of the diagram. Okay, so the reason why there are two delay lines for waves going on the right and two delay lines for waves going on the left here is because we want to be able to introduce energy or to capture energy at the middle of the string or at any point on the string. So basically, what these two data lines on each side of the diagram are going to allow us to do is to get the sound in the waveguide in different position. You know, like, so basically, by diminishing the size of the data line that we have here, we're going to be able to get closer to the left side of a potential string, for example, or a tube. And well, here it's a string because of the phase inversion at the extremity. I'm about to talk about that. And then on the other hand, if the data lines here on the left are getting longer and the one on the right are getting shorter, we're basically going to pick up sound closer to the right side of the string. So basically, what these two couples of data lines are allowing us to do is just to change the pickup position on the string. So we have waves going on the right, we have waves going on the left, but then we need to implement reflections at the extremities of the string. Because if you just take a string and you don't stretch it between 2 points, if you pluck it, it's not going to make any sound, because you need to have reflections on each extremity of the strings in order for it to actually behave and sound like a string. And that's what those two multipliers that we have on each side of the string are for. And you see that they implement literally just a sign inversion, so just a phase inversion of the waves at each extremity of the strings. And that's because the waves in a string are transversal waves, you know. And so when you get to the bridge, when the wave actually gets to the bridge of the string, then the string is going to go up and then it's going to go down like this, right? And so this literally just corresponds to a sign inversion. And we need to do that on the two extremities of the string, so on the left and on the right. And so basically what we see here is a very, very primitive, simple string physical model using waveguide synthesis. So one thing that is very important in waveguide modeling is this concept of bidirectionality that is very obvious here. We have things going in one direction and we have things going in the other direction. So going from left to right or from right to left. And so whenever we implement a physical model of a musical instrument, we're going to have to keep this bidirectionality all the way from the top to the bottom of the model. So for example, if you think about a violin, for example, or a guitar, so the string is connected first to the nut, so to the top, to the top of the bridge of the guitar, and then connected to the bridge itself, and then connected to the body of the guitar, right? And so all these things are coupled together. And because they are coupled together, they need to interact with each other, and that's why we need these type of bidirectional connection. So for those of you who already know Faust, you probably know that creating this type of algorithm is not necessarily very simple in Faust. Because in Faust you have the concept of feedback. So if you want to have a signal going in one direction and in the other direction, the only way you can do this in Faust is by using feedback and the tilde operator for that. And so that's how all the physical models of the Faust SDK were implemented. Most of them have a tilde and a feedback, which allows you to implement the waveguide. But if you want to create a system where everything is modular, so where you can put, say, a string here and then a bridge and a plug somewhere else, and you want to create a library which is completely modular in that sense, this is way more complicated to do in Faust because of this tilde operator, which is not a modular operator somehow. So when we implemented the Faust physical modeling library, the first thing that we had to do is to come up with a bidirectional block diagram algebra in Faust. So a form of algebra that would allow you to create this type of bidirectional connection in a very easy way without having to think too much about that. And if you look at the slide here on the screen, this is what one of the most primitive elements in the Faust physical modeling library allows you to do. And it's the chain element, and it allows you to create this type of diagram and this type of algorithm. So you see here that you have waves which are going from right to left. You have waves which are going from left to right. And you also see that there is a third channel, which is for the output. Okay, so some of you at this point might be wondering why we have that. Well, it's very straightforward, because if you go back to the previous slide, you see that if you want to get the signal of something in the middle of the block diagram, and if you want to bridge it to the end of the diagram, because in Faust things usually go from left to right, you need a third channel to basically get this output here and send it to the end of the algorithm, bridge it to the end of the algorithm. And so that's what the third channel here is for. Okay, so let me give you a little demo of how this works in Faust. So basically, in Faust, you can use the PM.chain element. So PM is for physical modeling library, right? And so you have the chain function in the Faust physical modeling library, which allows you to create this type of bidirectional connection. Okay, so each element you're going to put in this chain has to have 3 inputs and 3 outputs, right? So one input and output for left to right, one for right to left, and one for the main outputs of the algorithm. So here what I'm going to do is that I'm going to create a multiply block. Okay, and so in this block what I'm going to do is that I'm going to multiply signals going from left to right by say 2, signals going from right to left by 2 as well. And then I'm going to leave the third channel just as a signal like this, because currently we don't really need it. And then I'm going to be able to call that in multiply block, and I'm going to call it in PM.chain. Okay, and so here you can see the block diagram of this operation, which just looks like what we are expecting at this point. Okay, so now I'm going to create another block. Okay, and this block is going to be, for example, a delay block. Okay, and same thing, it needs 3 inputs and 3 outputs, and so I'm going to add a 10 sample delay. And here, of course, I assume that you know Faust already a little bit, so I'm not going into too much details in here. And so we have a second element here, which is for the left going for waves going from right to left. And finally, I'm gonna just leave the third third signal here empty, and now I'm gonna connect delay block to multiply block. Okay, and so now you can see on the block diagram that we're creating something which is a little bit complex, but what this is doing, is literally just connecting things as you've seen it on the slide here, and so basically the first elements in multiply block and delay block are connected to each other. Same thing for the second one, and then we just assume that things are going in one direction and in the other direction. Okay, so this is very useful for what we're going to do next. So I hope you sort of get what I'm saying here, because this is really important. So typically in waveguide physical models, you're going to have things going in those 2 directions, but then you're going to need terminations so that you create some kind of loop, as on the slide with the string. Like you have those 2 terminations, the -1 and -g, and so eventually you want to be able to add that to your algorithm. And so the way you do that kind of stuff in the Faust physical modeling library is by using the L termination and the R termination functions. You can see here on the slide how they work. They take two arguments. So L termination takes an element A and an element B. And the element B can literally just be a chain or anything you want to give to it. And A is the actual termination. And same thing for R termination, but it works basically the other way around. So here is how we're going to use that here. By the way, the algorithm we're implementing here is completely useless. It's just like to sort of give you an easy to understand example of how these actually work. So here I'm going to call PM.L termination, and PM.L termination expects two arguments. You remember there is one which is A and one which is B, and A is the actual termination. And here I'm just going to multiply the signal at the termination by -1, just like what we've seen on the block diagram of the waveguide. And then here, I'm just going to use a basic block, which are just 3 signals in parallel, basically, to make the system happy. So in practice, this element here is kind of useless, but we actually need to put it here if we do want things to work. Oh yeah, and of course, L termination needs to be fixed here. Okay, so here is the final product for this. So you can see that on the left side of the block diagram, we do have now a left termination. So everything that is going to the extremity of the waveguide is going to be multiplied by -1 here. And if we wanted to add a right termination here, we just have to do the same thing but the other way around. So we would call PM.R termination, and then we give a basic block here as the first argument. So we're gonna call it basic block, okay, and then here we can do multiply by -1 again, for example, and now we have a right termination. Okay, so in practice, this is an almost complete model, and then if you want to end the whole system, because we still have 3 outputs, so we could literally just reuse this element in another chain if we wanted to, because we still had 3 inputs and 3 outputs. Now you can use PM.end chain to basically complete the algorithm, and now you only have 1 output and no input. Okay, so now we're going to try to make something a little bit more useful than the previous example. So just before we move to that, I just wanted to sort of give you a very, very brief tour of what's in the Faust physical modeling library. So if you go on the Faust library's documentation website, and if you look for the Phys models library, which is right here now on the screen, here on the left, you get an overview of the different functions that are available in the library. So the functions that we use so far are all in the bidirectional utilities section here, and you'll find the L termination, the R termination, the chain as well as many other things. But then as you start scrolling down, you will find elements which are much closer to musical instrument parts. So you will find a nylon string, you will find a steel string, you will find guitar nuts, you will find all sorts of musical instrument elements, basically, that can mostly all be used inside a chain to design musical instruments. So here you have the bowed strings section with the violin bow, you have the violin nuts, same thing for wind instruments here, etc., etc. So once again, the idea here is really to be able to take an element implemented in this library and then to use it in a chain to create new kind of musical instruments using physical modelings and waveguides. Okay, so in the next example, we're going to try to implement a string instrument, a pluck string instrument, using the library. And for that, we're going to use a function which you can find in the string instrument section, and it's the open string pick. Okay, so that element implements an open string. Okay, so it means that the string is not terminated yet. It doesn't have termination, so it doesn't have a bridge or it doesn't have nuts. So that's still up to us to add those elements. And what it says is that it's a bidirectional block implementing a generic string with selectable excitation position. It has a built-in pickup whose position is the same as the excitation position. So you can change the position of the pickup and of the excitation, but they are the same in this function. Okay, and that's what the excitation parameter here is for. So we're going to use this function. Literally what it implements is the same thing as what we saw in the slide earlier in this presentation with the 4 deal lines, 2 in parallel of each other, as we saw earlier. So let's try to use this, and so I'm going to start completely from scratch here in the Faust web IDE, and I'm just going to create a new process line here, okay, and okay, so now the compiler is happy, and the first thing I'm going to do here is I'm going to create a function, and I'm going to call it myString, okay. And this function is going to have some elements, and I'm already going to use the with environment here because this function is going to have a fair amount of local functions, okay? And so I'm going to call it here on the process line, okay? So currently I'm doing something completely empty, but I'm starting a string, basically, and I'm going to use the Faust physical modeling library to implement that string. Great. So the first local element I'm going to declare here is going to be a chain. Okay. So I'm gonna call this okay, my chain. Okay, it's a very bad name, but I'm gonna start by this. Okay, and this chain is going to use the chain element from the Faust physical modeling library. Like this. Okay, and so in this chain, I'm going to have to put some stuff, and the first thing I'm going to put is going to be an open string. And so I'm going to use the function that I just talked about, which is the open string pick function. Okay, and if we go back to the documentation, the open string function has 4 parameters. The first one is the length of the string in meters. And that's kind of a standard in the Faust physical modeling library. Usually you declare length and sizes using the metric system, and most of the time you use meters. You always use meters. The next parameter is the stiffness of the string between 0 and 1. The next parameter is the pluck position. And finally, the last parameter is the excitation. So the excitation itself. Okay, so 4 parameters. So first here, I'm going to declare a variable that I'm going to call string L for string length. And for now, I'm just gonna actually declare it here, and for now, I'm gonna say that the string is 1 meter long, which should make like a reasonably pitched string. Okay. The next parameter is the stiffness, and I'm declaring it here. Okay, stiffness, and I'm gonna say that stiffness for now is 0.05. By the way, like all these values are kind of empirical here, you know, like basically this is just a value for some kind of low pass filter inside the string, you know, like so here I don't want it to have too much impact, so I'm just going to put 0.05 here. Okay, the next parameter is going to be the pluck position. So if we want this to sound sort of like an electric guitar, it's good to put a pluck position close to, say, 0.3, you know, because it's sort of like a third of the way on the guitar string. Okay, and so so I think pluck position is a parameter that I want to make available here for people to control once the function will be actually completed. So I'm going to put it here. Okay, and finally, the excitation. So of course, in this scenario, the excitation is going to come from the outside of this function, and it's probably just going to be an impulse. So I'm going to put it here as the last parameter of the function. Okay, and okay, so now the chain has an open string. Once again, that open string is what we want, but it's not terminated. It's open. So we still need to add a nut and a bridge on the other side of the string. Okay, so here on the left side, which we will consider here to be the top side of the string, we're gonna add nuts. Okay, and believe it or not, but in the Faust physical modeling library, you can already call PM dot elec guitar nuts. Okay, and this should just work. So now our chain has electric guitar nuts on one side. There are different types of nuts. There are acoustic guitar nuts, and so here we're using the electric guitar ones. If we had more time, I would show you how you can actually implement those, but we don't have time for this here, so I'm just using the existing function. If you're curious about how all these things are implemented, you know that the source code of the Faust libraries is actually available on GitHub. So if you go on GitHub and you look for physmodels.lib in the Faust libraries repository, you will find the source code of all the functions that we're using here. You know, so if you do a search on this page for say elec guitar. Oops, sorry. Elec guitar nuts. There we go. Elec guitar nuts, and you see the source code of elec guitar nuts here. Okay. So if you're interested, you can always check the source code of all these functions to know what's in there. Okay, so on one side we have nuts, on the other side we need a bridge. So here I'm gonna call the function called elec guitar bridge. And so now we have a string which is terminated. And if it's terminated, it means that it can actually make sound, which is what we want here. Okay, so great. So at this point, I think all we need to do is to actually give some values to the parameters that are not configured here yet. And so I'm going to configure the pluck position to be, say, 0.3, as I said earlier, because that's a value that makes sense in that context. Okay, so now we have the string. We have the string, but we need to excite it. And to excite it, we're just going to create an impulse that we're going to send in the string. There are much more sophisticated functions to do that kind of stuff in the Faust physical modeling library. You know, there are excitation models but we're not going to use them here because, once again, like the goal of this tutorial is to sort of give you a sense of how all these things work. And so if you're interested in that, like you can just go back to the library's documentation to see how these things can be used. Okay, so here I'm going to create a button because we can do that in Faust, and I'm going to call it gate, of course. That's kind of a standard in Faust for a trigger. So I'm I'm calling that one gate here, and I'm going to use the impulsify function. Impulsify function that basically turns the signal from a button into an impulse, right? I'm sure many of you already used that function before. And finally, I will just connect that to the string. Okay, so now we have an error here. And yes, well, I think there are multiple problems here. The first one is that in my myString function, I actually didn't call anything here yet. So I do need to put my chain. I'm sure some of you already caught this earlier. And okay, now I can see that I misspelled guitar bridge. Okay. Yeah, and so we still have errors because there is another thing that we haven't done yet. And that thing that we haven't done is that we need to terminate the chain. So we already did that in the previous example. And so in Faust, in the Faust physical modeling library, whenever you have a chain, you need to terminate it using the end chain function, and that's what I'm using here. Okay, and so now Faust is happy, and we do have something happening here. Great. So in theory, it should make sound. So if I run it, and apparently it didn't crash, and I click on the button, I do have a beautiful string sound. Okay, if you want to have it on the two speakers of your computer, you do need to do this, right? So that the output of the string is split, and that it goes on the two speakers of your computer. Nice. Okay, so now if we want to make this a little bit more controllable, we want to be able to control the string length in real time, right? And potentially assign a frequency to it. So how would that work in the Faust physical modeling library? The first thing we need to do here is, of course, to create a parameter for this string to control the length outside of the function itself. Okay, so here I'm going to create a length parameter, and this is length. And I'm going to pass it to string L that I have here. And now some of you might be wondering why I'm not just using length directly in here. Well, it's because in Waveguide modeling, depending on what you put in the chain, because everything works with delays, especially the filters that are used to implement the electric guitar nuts or the electric guitar bridge. Because of all these extra delays, the string tends to be detuned a little bit, or at least out of tune. So the reason why I'm adding this extra step here is so that we can tune the string by hand, basically. Potentially, that needs to be done. Okay. So I'm going to show you how to do that after that. Now I just want to please the Faust compiler by basically setting up the actual length here. Okay, so I'm going to create a variable. I'm going to call it L. I'm going to say that L is equal to 1. Okay, and I'm going to pass L as a parameter to my function here, and in theory, still makes sound. That's great. Perfect. Cool. So as I said, the string here currently is out of tune. So the only way to tune it is to tune it by hand, and so you just want to take a a sine wave at 440 hertz or a pitchfork or whatever you want, and you need to tune the string until it has the right pitch. And so here, I already did it before doing this presentation, and I know that I have to subtract 0.11 to the actual length to get the right pitch. So you see that there is actually a fairly significant difference here between what we're expecting and what we need. Okay, so now it should be in tune, and maybe it's not completely in tune. And if it's not completely in tune, you can adjust the value of this parameter here. But once it's adjusted, it will be in tune for all pitches, of course, right? Okay, so finally, I want to control L with a slider. So I'm gonna create a slider, and I'm gonna call it freak, okay, in case I wanted to have a polyphonic string, because I will have freak and gate. You know that, right? And so for default, I'm gonna say 400, minimum I'm gonna say 100, maximum I'm gonna say 1000, and precise step of 0.01. I'm not explaining what I'm doing here because, once again, I sort of expect that you guys know Faust already, and so I'm just moving forward here. Okay, and so now how do I convert this frequency into a length? Well, there is a function for that in the Faust physical modeling library, and it's basically F2L. Okay, so now I have the slider, and I can control the pitch of the string that I'm playing. And so we have a string, and we could easily add a gain slider that we would multiply to the output of Impulsifier, for example, and then we could totally play that string with a MIDI keyboard. I'm not going to do that now because we're constrained by time, and I just want to move forward to the next topic. But that could be a nice exercise for you at this point. Okay, so this is sort of the very general idea of how the Faust physical modeling library works. And of course, you can make things that are much more sophisticated and much more complicated. And in fact, it would be interesting here to go into more details to see how wind instruments are implemented, because it's slightly more complicated than just with a string. But the idea is always the same. You use a chain and you put the different instrument parts in your chain. You connect them to each other's, and then you create a function around that, and in theory, in the end, you get sound. So the idea is always the same, and you can implement most musical instrument using this system. Okay, so now in this last session, I'm going to show you how to use Mesh to Faust to create physical models compatible with the Faust physical modeling library using Mesh to Faust and using 3D meshes, so basically 3D graphical objects. And you'll see that it's actually fairly easy. In fact, the hardest step here is to install Mesh to Faust on your computer. And I'm not going to document that in this video because you can find these informations on the Faust website. Okay. So here I'm going to use various softwares, and I didn't necessarily told you to install them before this presentation, but you can easily find them on their respective websites, and you can find these informations in the slide that is currently being displayed on your screen. Okay. So the first software we're going to use here is Openscad, and Openscad is one of my, it is not one of my, it's my favorite CAD modeling software. I've been using many CAD modeling software like SolidWorks, Rhino, and blah, 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 and Openscad is open source and it's free. It's very, very basic, very simple, but you can really do crazy things with it. It's super powerful. So if you don't know about it, I recommend you to give it a try. Okay, and it's also based on a functional programming language, which makes it great and really relevant to what we're doing here. Okay, so when you have Openscad, you just create a new model. And so the goal here is we're going to model a metal plate in Openscad, and then we're going to try to make a physical model from it using Mesh to Faust. Okay, so it's very easy to make such a model in Openscad. Okay, let me scale that up for you here, because all we need to do is to create a cube. And we need to give it dimensions. And the dimensions here are going to be in millimeters. So I'm going to say that I want a plate, which is going to be 400 millimeters by 300 millimeters. So 40 by 30 centimeters. And for thickness, just 5 millimeters. Okay, and you need a semicolon here. And if you render that object, okay, there we go. We have our metal plate. Awesome. So, this is a very simple example, but it's just to show you how this works, so we're done with Openscad. We did what had to be done. Then in Openscad, we need to render, so basically mesh that object, which is something we're going to do by clicking this button here. Okay, so this is done. Can take a lot of time if the model is a complex model. And then we will export that to STL, and STL is a very standard format for that kind of things out there. And okay, and so I'm gonna, oops, no, that's not the right folder. Today it's not the Power Workshop, it is actually the Faust PM Workshop. Okay, and so I'm gonna save it here, and I'm gonna call that plates.stl, and I'm gonna save it. Okay, so now we're done with Openscad. So you can save the model if you want. I'm not gonna do this, I'm just gonna get rid of it because we have our plate.stl, and that's what we want to use. The next software we want to use here is MeshLab. And we're going to use MeshLab for a very specific reason, because you'll see that the mesh that was created by Openscad here is a highly optimized mesh. And the problem of that kind of mesh is that it's not going to work for finite element analysis as we're going to do it with Mesh to Faust. And so here I'm going to get back to Faust PM Workshop, to the model that I just had, and I'm going to drag and drop it in Mesh Lab. Okay, just say okay. Now we have our plate, which we already had earlier. Okay, so this is our plate. And so in Mesh Lab, you can actually plot the triangles which constitute the mesh, and you see that for the top surface here, there are only 2 triangles, and that's what I meant by optimized mesh. Here, instead of having this, we want to have many small triangles that constitutes the mesh, because we need to have like a high density mesh, which is not what we currently have here. So to do this in MeshLab, I'm going to use a filter, and so this filter is going to be found in the remeshing functions here, and so here what I want to do to increase the number of triangles that I have on the surface is uniform mesh resampling that you can find, I think, right here. Uniform mesh resampling. Great. So basically, the smaller this number here, the more triangles you will have in your mesh. And so for that example here, I'm gonna set this to say 3.5. I think that's the value that we want here. So, you know, you can play with that. You know, like here I'm putting 3.5. Actually, you know what? I'm going to put 4 just to be sure. And then I will just say apply. Okay. And now here in this window, I have a new mesh which was created. So I'm going to close the filter. And I don't remember which mesh is which one. Okay, so I think because you can hide meshes, and so here if I plot, yeah, there we go. So now you can see all the triangles, and yeah, okay, this one is the new one, and this one is the original one. So I'm gonna actually get rid of the original mesh. So I'm gonna say delete current mesh. Okay, and now I have this new mesh, which is relatively high density with a lot of triangles, and that's what we want to do finite element analysis here. Awesome. So there are other things that you can use here and other approaches to increase the density of your mesh and just like remesh it. I'm not going to go into details here, but this is all documented on this website here that is displaying on the screen. And you can find more information about other techniques in MeshLab to increase the density of the mesh. Great. So we're almost ready to turn that into a physical model. The one thing that we need to do first is we actually need to scale that model down. Because the problem is that it's too big, and so right now the unit is not right basically, and so we need to scale it by a factor of 0.001. So here I'm gonna go in filters, and in filters, yeah, I'm gonna look for normals, curvature, and orientation. And I will then look for transform, and for transform, I'm gonna select scale. Okay, and so here I'm gonna scale the x-axis by 0.01, which will spread to, because I'm doing uniform scaling, so it will spread to the other axis. And then I can just do apply, okay, and then it will just disappear because now it's very tiny. Okay. So what I'm going to do now is I'm going to export that mesh as a .obj object, because that's what mesh to Faust is going to take as an input. And so I'm going to call my model plate.obj, okay? And then I will save that, and I will say okay, and we should be done. Awesome. So now I can close MeshLab, and I have my .obj object here. Okay. So the next thing I need to do is to actually use Mesh to Faust, and Mesh to Faust is a command line tool, right? So you need to use your terminal to use it. It comes with a Faust distribution. You can find it at the URL below in the Faust distribution, and you need to read the README to know how to compile it and then install it on your computer. I'm warning you, it's a pretty heavy tool because it relies on the MKL Intel library, which can be a pain to install on some platforms. On Arch Linux, it's super straightforward because it's part of the package manager, but on other platforms it might be really rough. So I'm warning you here. Okay, so I'm gonna go in the folder where I saved my .obj file, and it's the Faust PM workshop folder on my desktop. Great, and okay, so I have the plate.obj file right here. Okay, so all I need to do now is to call mesh to Faust. And I'm gonna provide first mesh to Faust an input file. So I'm gonna say in file, and here I'm gonna use plate.obj. Okay, then I will specify the number of modes that I want to synthesize, because this is basically going to create a model synthesizers. Okay, and so here I'm going to say that I want only 50 modes. So the higher the number of modes, the more computation it's going to take, like, so 50 modes means 50 bi-quad filters, like, so that's already a lot, so depending on the kind of application that you want to do here, you might want to decrease or increase that number. Okay, then I will specify the number of finite element methods modes. So basically the number of internal modes when Mesh to Faust is going to compute the modes for the model. Okay, I'm going to say that the max mode, so the maximum mode, the highest mode, has a frequency of 10,000 hertz. So I'm telling the system to ignore all the modes that are above 10,000 hertz, so 10 kilohertz. Okay. Then I can specify the excitation positions that I want to integrate to the model. So how do I figure that out? So actually, if you reopen MeshLab on your computer, and if you drag and drop the plate.obj file that we created, great. Then you plot the grid of the model. So if you click here on get info, you can select any position on the model, and then it will give you the ID of the vertices corresponding to the triangle that is selected. So here it's very small and tiny because I have a high resolution screen, but I think if you press the P key on your keyboard, it will actually output all the informations that you need here. So you can select as many excitation positions as you want, and what you want here is to take one of the vertex position on the model here. So you see that here there's one that is 10,149, and that's the number that you would want to put in the terminal here. Okay, so I'm going to close that now. Okay, I'm going to put something fairly random here because we don't have a lot of time, so I'm going to say 5483, so 2 positions, and the other one's going to be 69 and 6959. Okay. Okay, I'm gonna say that I want this to be in debug mode so that more informations are plotted as the model is generated. And finally, I need to specify the material properties. Okay, and so you can find material properties easily pretty much anywhere on the web for wood, metal, any kind of material. And so the values that I'm going to use here correspond to copper, I think. So it's a very soft metal. And so if you want more information about this, just look at the documentation of Mesh to Faust. And so, yeah, these 3 values here correspond to copper. And finally, I want to specify the name of the model, and I'm going to call it plate. And then I can just press return, and the model will start being computed. That operation might take a little bit of time depending on how powerful your computer is. On my computer, it took about 5 minutes. In some very large models, it can take hours, so just be ready for it. And during those hours, your computer might run out of memory, and then it might just stop. Okay. So at the end of this operation, you end up with a .lib file. And so it's a Faust file. So you can open it, look at its content, and basically that's your model, model. Okay. So here, just to demonstrate this, I'm just gonna actually take this, copy it. Okay, so I'm selecting everything, I'm copying it. And then I'm going to create a new file in the Faust web IDE, and I'm going to paste the content of the .lib file in the Faust web IDE. So it's a .lib file, so it doesn't have a process line. And so I'm going to have to add the process line here. So I'm going to say process, and process is going to be equal to my model, which is plate. You know, that's the name that I specified in the previous step. So this is plate, okay. And plate has several arguments, and the first one is going to be the excitation position. Remember, there are only two because we only specified two vertices on the model. So for now, I'm going to set that to 0 because we just want to hear sound here, right? So I'm going to set that to 0, and then you can specify values for the T60, which is the time of resonance of the model, and that's something that Mesh to Faust is not going to compute for you. So you just need to put like empirical values here, which kind of sucks because there are ways to solve this, but we never actually had time to work on it, and it's a complicated problem. So here I'm going to say that I want to have a maximum time of resonance of 8 seconds for the model. And then for the other values, I'm going to put 1 and 1. And there are just like decay ratios for the time of resonance for high frequencies versus lower frequencies. Okay. So now Faust is happy and I need to drive the model. And to drive the model, I'm going to do the same thing as in the previous example that I gave you. I'm going to create a gate button, and I'm going to send that through an impulsify, and finally to the plates. Okay, and now if I run the model, and if I click on the button, beautiful, I hear my plate, and I'm going to send it to the two speakers on my computer here. Beautiful, great. So that's the plate. Okay, well, I think I told you everything I had to tell you for this tutorial. So you will be, of course, able to rewatch this video after the workshop. I hope you guys are having a great time today, and you can find more information about all these tools on the web because they are, of course, completely open source. So thank you very much, and I will now take questions on the chat.